So we're finally done with the binary search trees. And starting from today and also in the next week, we're going to talk about some priority queues, or say the heaps. So today's topic is about leftist heaps and skew heaps. We put them together because they are closely related. Actually, their relationship is pretty much similar to that between the AVL trees and splay trees. We'll see. So let's start from the leftist heaps. So what should be the first natural question to ask? Why? Why do we have to learn this, right? Oh, by the way, do you still remember what a heap is? A heap, also called a priority queue, right? It's a queue that accepts normal in-queue operations, but the DQ is different, right? So for every DQ, we're supposed to return the element with the highest priority, right? So it depends on how we defined the highest priority. It can be the element with either the largest key or the smallest key. Here we would just take the smallest key, for example. So in the fundamental course, we have learned how to use an array to implement a heap, right? So to store a complete binary tree in an array, right? You still remember that? But please be aware that this is not the only way of implementing a heap, okay? Well, a complete binary tree is a pretty smart solution in the sense that since the tree is almost perfectly balanced, operations like insertion, deletion can all be done in log n time, right? Then the question is, why do we need some other form of heaps? Well, the reason we need a new structure to represent a heap is that besides insertion, deletion, and find, there is another operation that is also commonly used, that is merging. Or say, in other words, given two heaps, we're supposed to merge them into one. And so the target of a leftist heap is to speed up merging in linear time. First of all, let's have a quick review about the structure of an ordinary heap. Okay, and there are two kinds of properties that a heap must have. The structure property means that it's stored in a complete binary tree. And the other property means that the key value in each node is no larger than, smaller than or equal to the key values in its children if it's a min heap, or say no smaller if it's a max heap, right? Now, here comes our today's first discussion topic. How fast can you merge two heaps if we simply use the original heap structure? Now I'd like you to pause the video and think about it. So what would you do? One very simple solution is simply to copy both heaps into one array and call build heap, right? Do you still remember that linear algorithm? I mean, the algorithm that builds a heap from bottom up, right? That we keep adjusting the subtrees from the lower right corner and step by step up to the root. And the time complexity of that algorithm is linear, big O of n, right? So does it mean that we are done? See, we already have big O of n here, right? But wait a minute. Since we must copy one array into another, it is big theta of n, not big O of n. We want n to be an upper bound, but certainly we hope to have a faster algorithm that runs faster than n. So another direction to go is, how about using the pointers? With the pointer implementation, we don't have to copy. Instead, we can just change some links, can we? Well, the disadvantage of using pointers is that it'll slow down all the operations, because while we're moving up and down in an array implementation, it's only a matter of calculating the parent, which is a divide by 2, or a child, which is a times 2 or times 2 plus 1. It's left child or right child, right? So which can be implemented by actually a very simple bit shift, right? Shift one bit to the left or shift one bit to the right. It corresponds to times 2 or divide by 2, right? So it's quite fast if we implement it by an array. But if we use pointers, finding the next position following this pointer takes much longer time. Since the data are not stored sequentially means like they are stored one next to another in an array. If they are not stored that way, they might be scattered everywhere on the disk or in the memory. So it takes time to find the next one following a pointer, and therefore using pointers are more expensive, or say slower. So if we decide to use pointers, we better have a complexity that is better than big O of n to compensate the loss of speed. So here we are, the leftist heap. Say it has the same other property. That is, every key is either smaller or larger than its children. That's the other property. But it has a very different structure property. It's still a binary tree, alright, but it tends to be very much unbalanced. Judging from its name, it's called leftist heap. It will be a tree that tends to be skewed to the left. So it's nothing like a binary search tree that we will prefer it to be as balanced as possible. Actually, a skewed tree would be its best case. Now let's see why. So in order to understand leftist heap, we must define a special term called now past length first. Just similar to while we were studying AVL trees, we defined a BF, right, as balance factor. And while we were studying like red-black tree, we defined black height, BH, right? So for leftist heap, we define NPL, that is the now past length of any node X. It is defined to be the length of the shortest path from this X to a node without two children. So to a node that is either a leaf node or a degree 1 node. Okay, and a now pointer's NPL is defined to be -1. So here comes my question. Given the heap, how are we supposed to calculate the NPLs of each node? Is it calculated from bottom up or from top down? Now think about it. From bottom up, right? Because one thing for sure is that for the now pointers, the NPL is -1. If we know the NPL of the now pointers, certainly we can obtain the NPL of all the leaf nodes, right? And if we know the NPLs of all the leaf nodes, we can move up to calculate the NPLs of their parents, and so on and so forth, right? So here comes the calculation. So the NPL of any node X can be obtained from the NPL of its child, then +1. And if there are more than one child, if there are two children, we take the smaller one because it's supposed to be the shortest path. Alright? Now the leftist heap property is that for every node X in the heap, the now past length of the left child is at least as large as that of the right child. At least as large as means what? Means greater than or equal to. right? Means its left subtree is greater than or equal to its right subtree. Means it tends to be skewed to the left, right? Now let's have a look at the two cases. How about this one? First, let's calculate the NPLs from bottom up, right? For this leaf node, obviously the NPL is 0, right? And how about this parent? If from this child is 1, but it has no right child, so it's a null pointer which is -1, and therefore we take the minimum. This is 0, and this is 0. And how about that one? It's going to be 0 plus 1, that's 1, alright? And how about this one? This is obviously 0. And how about this one? We have two values, either 1 plus 1 or 0 plus 1, and we take the minimum, the smaller one, and therefore it's supposed to be 1. So is it a leftist heap? Yes, no problem. Okay, now let's check this one. We have 0 and 0, so this is going to be 1. But that one is 0, so something's wrong here, right? But let's continue to calculate this one. The NPL of this one would be still 1. And this is 0, and that is 1. Okay, so is this a leftist heap? Well, since this node violates the leftist heap property, this is not a proper one. Alright, so according to this property, we realize that the tree is biased to get deep toward the left. Biased means what? In Chinese we say it's 偏心的，就是我们更偏向于向左延伸。Actually, a tree which is skewed to the left will be the best case for the leftist heap. Let's see how come. Here's the most important theorem. We say a leftist tree with R nodes on the right path must have at least 2 to the power R, then -1 nodes. And the proof is simple by induction. It's given in your textbook. My question is, so here comes your next discussion question. How long is the right path of a leftist tree of n nodes? And what does this conclusion mean to us? Now I would suggest you to pause the video and take a few minutes and think about this question. So the first question, how long is the right path if we have n nodes? According to this theorem, R is the right path length, right? If the right path length is R, then we must have at least that many nodes, which means that n must be greater than or equal to 2 to the R minus 1, right? So we have an inequality like n is greater than or equal to this number, and we add 1 to both sides, we get n plus 1 greater than or equal to 2 to the power R, and let's take a log from both sides, and we get something like R is smaller than or equal to log of n plus 1, right? That's very important. It means what? It means that if we have n nodes in a leftist tree, then its right path length is at most log n. So the leftist tree of n nodes has a right path containing at most log of n plus 1 nodes, which means the right path length is big O of log n. So what does it mean to us? It means that the tree is skewed to the left, alright? And it's guaranteed that its right path is always quite short, is bounded above by log n. It means that if we can get everything done along the right path, then it's guaranteed to be short, to be big O of log n. So hopefully, while we're merging two heaps, if all the work can be done along the right paths, then hopefully the time complexity is better than big O of n. It's going to be big O of log n. That's the good news. And among all the operations, the troublemakers are insert and merge. But insertion is merely a special case of merging, right? It's like to merge a special heap of only one node into another heap. So we just concentrate on merge.